Good afternoon and welcome to the 21st annual exhibit of Hydrogen and Fuel Cell Technologies. We have done the gamut today. We have been discussing everything from the PEM electric cells, electrolysis, electrolysis, everything. And we're coming up to a mixture of topics. We'll have an update from AVL on solid oxide fuel cells and solid oxide electrolyzers in fuel cell engineering. Speaking to us will be Jürgen Rechberger, who's from AVL. Please welcome with me Jürgen Rechberger.
Okay, good afternoon. Thank you for the introduction. My name is Jürgen Rechberger. I'm from AVL, which is an Austrian company. And our main business is, so AVL is the worldwide largest independent engineering supplier within the automotive industry. That means we are developing together with the automotive industry, with more or less every car manufacturer in the world, powertrains. From conventional ones, engines-based, up to battery and fuel cell electric vehicles. So that's our background. We have since 2003 an activity towards fuel cells. It's also mainly based automotive, but we're also going into some applications towards stationary power generation. Okay. Should this work? Okay, now it's working. So I want to talk today about three different topics. We are, as a few people probably know, we are developing portable and mobile SOFC systems. We will come to that a little bit later. I'll give a short update on our stationary SOFC development and also about solid electrolyzer systems development. Regarding the portable or renewable energy system, what the automotive industry is looking into are at the moment these two paths. So we are looking into hydrogen mobility with mostly PEM fuel cells, and obviously the hydrogen will be, we need to get out of renewable energy via electrolysis. So that's the one path which we are focusing on with the Toyota Mirai, with the Honda, with Hyundai and all the others. Then, of course, we are going the way through battery electric vehicles. We should also use their renewable energy. And what we are suggesting is a complementary technology. So AVL is also working heavily on the PEM technology, but we are also working on a complementary route, which gives us more fuel flexibility, and this is a solid oxide fuel cell. So what we suggest is a fuel flexible SOFC, because it can run with a lot of fuel feedstocks. So we can run SOFC, obviously with hydrogen. Most promising for it might be a biomass, so any kind of biofuels, ethanol, methanol, whatever, fuel based on biomass. And we can also, of course, use synthetic fuels out of hydrogen and some biomass. And obviously, of course, the technology also works with fossil fuels for some kind of transition phase. And where we do see the main applications for this, it's basically this four. So we are now heavily working on solid oxide fuel cell based range extenders for battery electric vehicles. And we have a few other applications. So that's, for example, the truck heavy duty idling, special purpose vehicles. So portable power generators are pretty interesting for off-road vehicles. And there's a big market also in the marine and leisure applications, for example, in camping, in boats or yards. So that's most interesting for us at the moment is truck anti-idling and battery range extender vehicles. And on these applications I will talk a little bit in the next slides. So on the truck heavy-duty idling, this is a quite interesting product because heavy-duty trucks on the United States are idled for around 8 hours a day to provide electricity to driver comfort functions, like auxiliary heaters, like air conditioning, micro oven, refrigerator. They have all this stuff in the truck and they need electricity for this. And at the moment they're doing like keeping the main engine idling, which is obviously not a very good solution. And therefore, we try to develop an APU, an auxiliary power unit, with 3 to 5 kilowatt, which will provide this electricity out of conventional diesel fuel, which is obviously on board. And for this application, we had a quite big project in the last years, and it was called DESTER. And there were 5 or 6 partners, European partners, developing this product and demonstrating it in heavy-duty trucks. And there were a lot of very nice achievements. So we have done a lot of durability testing with this technology. We have done a lot of vibration testing. And we also improved the SOFC technology itself significantly towards thermocycling and sulfur tolerance. We also, obviously, at the end of the project, did a vehicle integration. So we packaged the system to a packaging space which fits into the vehicle. You can see it on the picture. It has been completely integrated into the electrical system of the truck, and it provided the electricity for all the comfort functions. And this has been extensively tested. So for 5 weeks of permanent testing, the vehicle was on the road for all this time. And basically the project reached more or less all the goals. So we have reached the 3 kilowatt, we have reached the efficiency target. And what was very impressive, we measured in the vehicle a 71% CO2 reduction during the idling, which is really a significant improvement. Now let's talk about the second application, and that's range extenders for battery electric vehicles. So we're all aware of the issues of battery electric vehicles. So they have a limited range, there is a long low recharging time. We have issues with the recharging infrastructure. The connected load is an issue. We cannot everywhere install these chargers. It will cause with more vehicles some issues with grid stability. And of course, there's a cost issue. So this is basically the issues, what led us to a fuel cell-based range extender. And what we suggest is a solid oxide fuel cell-based range extender, because the main purpose obviously is to extend the range of a vehicle. We can reach up to 700 kilometers with this concept. We can use the existing fuel infrastructure, so this technology works practically emission-free with any kind of fuel. And we can diversify the energy sources for this. So there will be also, not globally, in all regions, we will see charging stations and we will see hydrogen infrastructure. So there will be regions without this infrastructure, and especially for these regions, we suggest a biofuel-based future. What are now the benefits of this concept? So it's obviously a very high range of a vehicle. It's up to 700 kilometers actually. We have no recharging times. We have a very fast refill. We have 0 or extremely low emissions, and basically no noise issues and no vibration issues. But of course there are some challenges. So there are the big challenges, power density, rapid startup. We need to start the system in a few minutes, and internal robustness of the technology. And these challenges are now addressed in very large projects, and there's also actually an automotive OEM involved into this. Where is the energy and CO2 potential of such a technology? So that's a typical result from this well-to-wheel analysis from the automotive industry. So we see on the x-axis the complete energy consumption, including the fuel production, and we see on the y-axis the GHG emissions, also including vehicle and fuel preparation. And in this we are in the lower left corner. So we don't have the conventional applications, the conventional engine-based solutions, because they would be far to the right. So we are really down in the lower left corner, and we see here only fuel cell solutions and battery solutions. On the fuel cell side, which are the blue dots, we see the fuel cell vehicle approaches with hydrogen from wind energy. On the upper blue dots, we see hydrogen from natural gas. And in green, we see the battery electric vehicle. On the lower left corner, we see the renewable electricity from wind. And the upper right dot for the battery electric vehicle is with the European grid. And where is now the suggested SOFC range extender? It's actually very attractive, because we are really here in the sweet spot. So we can really show a very, very high energy efficient solution at extremely low CO2 emissions. So we are somewhere in the range of 55 to 75 megajoule per 100 kilometer. Just for you to understand, at the moment a gasoline is at 200. So we are talking about a factor of 4 improvement. And from the GHG emissions, we are in the range of 5 to 15 grams per kilometer. And there we are at the moment at 140 with a conventional powertrain. So it's a significant improvement based on biofuel, and it's practically emission-free. And there are very big projects underway at the moment to develop this technology with an international, globally leading car manufacturer. And this is one of the first milestones. So we have already realized a proof of concept system running on biofuel. And based on that, we now will further develop this and integrate this already into the first concept cars. Then we change a little bit the topic. We come now to stationary power generation with SOFC. So we are also very active in this. And there is one interesting project underway, which is stationary power generation out of biomass. So we are developing at the moment a system, an SOFC power generation system, which is directly coupled to a biomass gasifier. So we gasify, for example, wood, and then bring this directly into an SOFC system. And with this, we want to show an electrical efficiency above 50%, which is very, very high based on the biomass. And what we already learned from that is that actually there's a big benefit doing that because we can dramatically simplify the SOFC system. So we didn't expect that at the beginning, but between these two processes, the gasification and the solid oxide fuel cell system are a lot of synergies. And if we bring them together, we can reduce the complexity and also lowering the costs of this. So these are more the interfaces which we see in the system. So we bring in here the exhaust gas from the gasifier burner. We bring in fresh air. We put in the cleaned wood gas from the gasifier. Obviously, we need some cleaning. So in the wood gasification, there are things in there which we don't want to have in our fuel cell. So we need to clean it. Especially there is some sulfur and some stuff like that. And there's the further interface with the exhaust gas to the gasifier heat recovery. What we're also working on is, so the stationary fuel cell industry is very much focused on natural gas as a fuel. So these systems are quite stable, they are running, they are sold in Japanese probably 200 times. We are now investigating into a fuel diversification. And we think it's very interesting to use also heating oil or diesel for stationary power generation with an SOFC. And so this is a R&D topic within AVL at the moment to realize a stationary SOFC power generation system based on diesel fuel or heating oil. And this is more or less the proof of concept for it. So it runs very, very stable. So we have realized a diesel steam reforming process, which brings us the total system efficiency also in the range of 50%. So we can also use now diesel in an SOFC power generation system with a very, very high efficiency. And actually the measured gas concentration from the diesel reforming process is pretty much completely in line with the expected simulation. A further topic we are working on is to couple SOFC power generation system with absorption chillers. So at the moment for SOFC power generation, mainly the electrical energy and the heat are of interest. But for a wide range of this globe, the heat is not interesting because we need cooling. And therefore we are at the moment developing an absorption chiller where we can directly transfer heat from the system into cooling. And this is more or less a straightforward available technology, but only in a very large scale. So you can purchase megawatt absorption chillers commercially, but they are not available on a smaller scale. And the power range we are here working is in the range from 5 to 10 kilowatt for T-central power generation. And therefore we develop at the moment with some academic partners an absorption chiller which we can fit to a 5 to 10 kilowatt SOFC power generation system. And this is actually here the picture of the first prototype. So this system is now running in a component test only for the absorption chiller, and we will integrate it with the SOFC system till end of this year and bring both subsystems together and into operation. Where we're also working on is to use SOFC with biogas, and therefore we also need some gas cleaning, and therefore we're also doing on the right picture some screening of adsorbent materials to clean biogas, and we use the same approach then also for cleaning the wood gasification gas. So especially the removal of sulfur and some chlorides is here in the focus, because this will cause degradation in the fuel cell. Okay, the last topic I want to give a short update is that we are also active on solid electrolyzer cells. So that means high temperature electrolysis. And this high temperature electrolysis has a few advantages compared to the state of the art. And the state of the art is alkaline electrolysis or PEM electrolysis. With the solid oxide fuel cell electrolysis, the energy consumed by the process is a little bit changed from electric power to heat. So we use with the high temperature electrolysis less electricity for the process and more heat, which can be beneficial. Also the efficiency potential is quite high, so we can reach similar or same efficiencies like in the PEM electrolysis. And there are two further advantages. One is that we can decouple the vaporization of water from the process. So we can use, for example, exhaust heat from industrial processes for the vaporization process. And a quite interesting advantage is that it can do co-electrolysis. So you can put in the solid electrolyzer cell directly steam and carbon dioxide to come out with a synthesis gas of hydrogen and carbon monoxide. And from that you can basically produce any kind of liquid fuel afterwards by a synthesis process. So these are the main advantages of the high temperature electrolysis, and that's the reason why we are looking into this. And there are also some good results available already. So that's an activity we have started probably 3 years ago. And we have set up here a project with our partners from Fraunhofer IKTS and Plansee, Montano und Leoben. And we addressed this from the cell to stacks to a proof of concept system in the laboratory. And you can see here on the right picture is the proof of concept system we built up in our laboratory. It was up to 5 kilowatt of electric power input. And we were really very, very happy with the result, because we have reached here more or less close to 80% efficiency in a first very small proof of concept system, which is a very, very good result and actually far beyond what you can do with alkaline electrolysis. So we will continue on that, and we will also look now into the development of a reversible SOFC SOEC system, so a system which can do both the fuel cell operation and the electrolysis operation. Okay, this was my last slide. Thank you very much for your attention, and if you have any questions, I'm available. Thank you.
Thank you. Do we have any questions from the audience? So two issues that came to mind when you were talking. One of them is, PEM cells and the automotive industry, they've been married for a long time. They're in bed together still. The problem with PEM cells, of course, is they don't like impurities, and solid oxide fuel cells allow you to use various sources of hydrocarbon. So the issue, though, has always been things like startup time, operating temperatures. So the question is, on the one hand, have you substantially reduced the startup time for mobile applications, or can you foresee that? And the other side of that question would be, well, I think that's enough for the startup time.
Of course, it's a very good question, and we are addressing it. So in this project regarding the SOFC range extender, we are developing a rapid startup stack at the moment. So we completely changed the cell technology from a ceramic cell to a metal cell. So we skip out 90% of the ceramics and put in a metal support. And we have then a metal support and only very, very thin ceramic layers. And there we definitely want to reduce the startup time below 10 minutes.
And reducing operating temperatures, there are so many solid oxide fuel cells with temperature ranges, they go way up or they go way down. If you were working towards an automotive application, would you try to lower operating temperatures? Does it matter at all in terms of efficiencies?
Not really towards efficiency, but of course it's a fact in the startup time. So we will lower it a little bit, but not too low, because with hydrocarbon-based fuels, we shouldn't go too low because we run into carbon formation issues.
Yeah. Okay. Very clear issues. This has been a wonderful talk. We should continue this, of course, but unfortunately we're out of time. We'll be approaching our next topic soon. Thank you very much, Jürgen Rechberger, who is from AVL List. You're on the fair. Where is your booth? Your booth is?
It's E55.
E55. Visit him there and continue the conversation. Thank you very much, Jürgen.
Thank you.
And thank you. We will be continuing shortly with a very important topic and debate. 9 of the toughest guys in the electrolysis industry will be up here to discuss the options in electrolysis and the applications. It's a very important topic because there is so much renewable energy available and there is just not the storage capacity to deal with it. So it's a central issue. In about 2 or 3 minutes, we'll start with that. I'm looking forward to it.